Okay, so hello everyone. Our group today will present the paper Multi-View Transformers for Video Recognition. This paper as of now hasn't been published. We'll just go over what all contents we are going to present right now before we move on to each and every category. So first, we'll go over a brief introduction of the paper. Then we'll see what related work has been referenced by the authors in regards to this paper. Then we'll go over the model proposed by the authors and the entire structure of it, and also the experiments which the authors have performed so that they can prove the superiority of their model. Then we'll go over the ablation study which the authors have performed in detail to analyze each and every component in their structure of the model. And finally, we'll conclude the presentation with a few thoughts. First, let's go over a brief overview of what this paper and the concept is all about. They propose multi-view transformers for video recognition. In this, they propose that separate encoders should be used to represent different views. So what's a view? We'll see that in detail later. Also, they have lateral connections to fuse information across these views or these encoders, so to speak. This model consistently outperforms better than the single view models which have been proposed till now, and also achieves state-of-the-art results on 5 standard data sets. And finally, it also improves the performance further when it is used with large-scale pre-training, as is the case with many other models. So the main concept of the model is as follows. So as we can see, there are multiple encoder blocks, and each encoder block takes a different type of input. Again, what this input is and all that stuff we'll go over later. Every block is connected to its neighbor by CrossView Fusion. Again, this is a concept which will be explored later. And the outputs of all these encoders in the multi-view transformer block are passed on to a global encoder, which uses it for further classification. So the USP of this paper is that there is no pyramidal structures or subsampling involved. Again, we'll go over that eventually. Instead of pyramidal structures or subsampling, they have multiple input representations or views. So basically, what are views? Views are tokens which have multiple temporal durations. Again, the structure of the token, etc., will be explored. But the reasoning we can go over right now. So according to the authors, there are majorly 2 types of tokens. The first one being long-term interval tokens, which according to them captures the gist of the scene. So for example, what's going on in the background or what's the entire point of a video and so on and so forth. The second type is a short-term short segment token, which captures fine-grained details such that it helps the model to perform better. Like for example, if someone is performing some gesture and stuff, so that will be identified by these short segment tokens. Before going on to the structure, let's go over the related work quickly. So they mentioned the related work in 2 segments. So the first one was evolution of video understanding models. Everyone knows that we started the video understanding models using 3D CNNs. They did a good job for their time, and they actually did come with a cost that they were resource consuming. So as and when people started realizing that attention mechanism is quite effective, they started inserting transformer blocks in these CNN structures. Until recently, when we got models like Vivid and Timesformer, which are completely transformer based without a hint of CNNs. The second part of their related work was multi-scale processing in computer vision. So they first started with what are these pyramidal or hierarchical structures. So basically, it is found very commonly in CNN models, which basically means that as and when the depth of a network increases, the resolution of the features decreases. A good example of a transformer network with pyramidal structures would be SWEN. Then they went to the slow fast model, which they say is very inspirational for their own model. So slow fast basically processes two inputs with two CNNs, which have different frame rates. And instead of different frame rates, these people use different views. Ultimately, they also mention spatiotemporal tubelets, which were first mentioned in Vivid, and they have used the token structure in their paper based on these spatiotemporal tubelets. So let's move forward and go over the structure of the model, which Sarath will take us
through. Guys, yeah. Now, before diving deep into how Vivid is working, now MBT is working, let's look at how Vivid is working. In Vivid, you have a video which is T frames. Let's consider that three frames are there in this example. These frames are embedded to tokens using an embedding matrix. And these embedded tokens here, for each frame, there will be n patches. And these n patches will be passed through a spatial transformer encoder. So this way, there are T such spatial transformer encoders, which are then passed through a temporal transformer, which models the relations between tokens across each frames. Next, there will be a classification, which predicts the action in the entire video. If you come to the idea of MVT, here, there is an input video, and the input video is divided into multiple views. As you can see, as an example, we have two views of the current video. And in each video, we have tubelets for each view. These tubelets, as you can see, are highlighted in red. These are then passed through, if you see that, these tubelets are very large. These large tubelets give rise to purely few tokens, and these large tubelets are needed to capture the long action in a video. These are embedded using a 3D convolution, so that we get the tokens. And while we have another view that processes the smaller tubelets, these tubelets will have more tokens. As you can see, tubelets are small and the tokens are large as compared to the previous view. Such tubelets are going to capture the fine-grained motion in the sea. After that, these tokens are passed through the multi-view transformer, as you can see. Here, these tokens are given a special naming convention. The tokens out of this embedding layer and passed through the 0th view are referred to as Z00, which means that it's a 0th layer tokens in the 0th view, and these tokens are called 0th layer and Vth view. As I have said, there will be a personalized encoder for each of these tokens. And here, if you see what is this multi-view transformer, this will have encoder blocks which are purely transformer based, and this contains only self-attention and not temporal attention, because there is already a global encoder which captures the temporal attention, and also there will be a CrossView Fusion. That's why there is no needed for other attention mechanisms rather than only self-attention. And there are L layers in each block. The striking thing to notice is that here the dimensions and the convolution matrix processed for the each view is different as compared to the other view. And we need a special mechanism to fuse the information between those. And let's see how cross fusion helps us here.
So can you see my screen?
Yes.
Okay. So CrossView Fusion is a method where the information coming from all these multiple views are exchanged across these encoders, which are specifically there for each view. So the others have invented 3 methods in order to do that. So the first one is CrossView Attention, and there is bottleneck tokens, and there is MLP Fusion. We'll discuss in detail about each of them. So whenever we talk about CrossView Fusion, basically we are trying to exchange information between all these tokens which are extracted from the multiple views. So the very straightforward method would be taking all these tokens which have been extracted from multiple views and apply self-attention on all of those tokens together. So that particular method is very computationally expensive, first thing, and it is very inefficient. So they have introduced CrossView Attention and the other techniques. So let's take a look at how CrossView Attention works. So in CrossView Attention, all these encoders are arranged in such a way that the view with the smallest number of tokens will be arranged in the initial layer initially, and then the view with the large number of tokens, they will be adjusted the last. So in terms of increasing order, we'll arrange all these encoders. And the information is exchanged between the adjacent pairs. And we'll look at how these information is exchanged between these two views, I and I+1. So initially, so there will be a input in the view I+1. So that is Zi+1, which will be taken from the self-attention block after taking the input here. So this particular Zi+1 will be taken and then it will be projected to a depth of Di. Why we are doing this projection is that we are taking the tokens from multiple views. So each view has a different dimensionality. So in order to match those dimensionalities, they have projected this Zi+1 and they have used Zi here. So they have used this Zi as a query and Zi+1 as key and values. So that's how they calculate the CrossView Attention. As its name itself, it suggests that across the views, they are taking the inputs and they are calculating the attention. So that's how they are generating that information fusing between these adjacent pairs. So there is an additional skip connection here in order to accommodate for the large scale image pre-training. So this is how they have calculated the CrossView Attention between these two views. So yeah, so the next one would be bottleneck tokens. In bottleneck tokens also, we arrange the views in terms of increasing order, and we exchange the information between the adjacent pairs. So what is the difference is that they have initialized a bottleneck token called Bi+1, and they have concatenated with the input of this view I+1, that is Zi+1. So after concatenation, we'll apply self-attention and then we'll pass it to the MLP head and we'll get the tubelets out of that. So in this tubelets, we'll be having the bottleneck tokens. So this particular Bi+1 will be projected to a depth of Di again for the dimensionality, and then we'll concatenate that with the input of a view I, that is Zi, and we'll do the same process all over again. We'll pass it to the self-attention and then MLP, and sequentially we'll get the output. So that's how the information is being transferred from view I+1 and view I here. So the next one would be MLP Fusion, which is a very straightforward technique. So here in MLP Fusion, what happens is that here as well, the views are arranged in increasing order and the information is being exchanged between the adjacent pairs. So here, what we'll be doing is we'll directly take the output from MLP block and directly we'll feed it to the view I just before the MLP block. So while doing that, again, we have to take care of the dimensionality and we have to project that Zi+1 to a depth of Di here and then concatenate them together and then apply the MLP layer on that. So that's how the information is being exchanged in MLP Fusion. So if you observe, one of the key factors or the key design in this particular three methods is that the views are arranged in terms of increasing order. The main reason that authors have stated in the paper is that it allows the encoders with the smaller views to accommodate all the information that is being carried from the larger views. So as we already stated that from the larger views, we get the fine grain motion. So all that fine grain motion is also accommodated with the smaller views. So that's how it helps them in order to have a better understanding between multiple views. So when we talk about where to fuse or where to make that connection between these two encoders, so it is not necessary to make that link between every layer of the encoder, because this particular fusion technique is having a global receptive field. When I say global receptive field, it says that even if you do at one particular point in I+1 and one particular point in view I, it's enough. The information will be exchanged across these two layers, across to these encoders. So where to exactly make that link is actually a design choice, and that is further analyzed in the ablation study. So information has been exchanged, everything is done between the encoders. So what next? So we have all the information fused between the encoders in this particular multi-view transformer. So after this, we'll be having outputs from each of these encoders. So output of each encoders will contain a classification token and a tubelet, just like VVT. So all these particular outputs of these encoders will be given as input to this particular global encoder here. This global encoder actually aggregates the information from across all the multiple views together, and it will generate a classification token out of that. So that's it. We'll look into further experiments that are carried by the authors in the next part.
Is my screen visible?
Yes.
Okay, so I will be covering experimental setup and part of ablation studies. So the training setup was very much same as Vivid. They were using synchronous HDD, momentum was 0.9, cosine learning rate with linear warm-up and so on. And other experimental setup was related to initializations. So we saw that there are two types of encoders, like view and global. So for the view encoders, they initialized using VIT pre-trained model on large-scale datasets. And whenever there was dimension mismatch, they used the projection mechanism of CVA fusion, which is already discussed by Abhishek. And for the global encoders, they used random initializations. They tested the architecture on pretty much the standard datasets, which are listed here. Now, before I deep dive into the ablation study, I would like to go through some of the notations used in the tables. So this is a sample architecture name that you will see in the tables. So here there are three parts, which signifies that there are three view encoders involved in the architecture. And each view encoder has a character and a number associated with it. So character is nothing but the type of VIT encoder, and the number is the size of tubelet. So in all the experiments, they did spatial crop of 16 cross 16. So this is the final token size. Now, there was some confusion in our previous presentation of Vivid between number of views and tubelet size. So to clear out that confusion, please observe this figure. So tubelet size is number of frames taking part in one token. So here the tubelet size is 6, and in below figure it's 1. While as the number of views is number of tokens required on temporal axis to cover the whole video. So basically, if you assume that this video had only 6 frames, so there were 6 views in the below figure and 1 in above figure. Now we can move to experiments. So first experiment was related to how complex encoder must be assigned to each view. So they started with assigning a complex model to large tube size as well as complex model to small tube size. And they found out that they were able to get better accuracy when a complex model was assigned to small tube size. But there was catch here. They were not able to rule out the possibility that this increase in increase in accuracy was due to this increase in G-flops or not. So they experimented further and were able to get the results where G-flops were similar, but the trend show was similar.
Like they were getting better results with the complex model assigned to small tube size. So this was the final model that was able to achieve the best accuracy. And the inference from this experiment is that the role of small size encoders is to get the granular details of the scene, and the role of large tube size encoder is to get the complete gist of the video. The next thought was, what if they assign complex model to all the view encoders? Will that help in improving the accuracy? So they did experiment, like this was the earlier model, but they assigned complex model to each of the views. So G-flops increased, but there was no bump up in the accuracy. So they found out, like even if they use complex model for all the views, it will be an overkill, and they are actually saving some computational complexity using their method. This is the same model from the last table with the best accuracy. And now let's discuss different fusion methods. We have already discussed what all methods were there. So now let's compare them. So this is the table where authors have compared all the models with fusion and without fusion method. Now please observe that there's only one view encoder in case of no fusion method. So the logic behind that is that there's no point of having multiple view encoders if there's no transfer learning involved. There's no connection in between them. So that's why there's only one encoder. And in below graph, there are multiple view encoders with all the fusion method listed. Now here we can see that there are two new fusion methods listed here. So let's discuss them. The ensemble approach is nothing but whatever probabilities are coming out of each encoder, they sum them all up and then pass to the global encoder. While as the late fusion was nothing but they took the final embedding just before the output, the final layer embeddings, and concatenated them and passed to the global encoder. So they experimented all this and they found out that CVA was the best fusion mechanism. So as the previous experiment suggested that the increasing number of views are helping them get better accuracy. So they wanted to know where to limit this number, how many views should be there. So they experimented and found out they were able to get bump up in the accuracy going from 1 encoder to 2 and then 2 to 3. But after that, pretty much the accuracy saturated. Here they had 14 view encoders, but there was no increase in the accuracy. So they finalized their architecture with 3 view only. So last experiment that they did was where exactly to put the fusion, what's the location. So they divided this analysis into 3 stages, early, mid, and late. So it's like 0th layer, 5th layer, and 11th layer of the transformer encoder. And they found out that individually, mid-stage fusion was the best. But they were also curious, like whether the combination of multiple can work in a better way. And yet, yes, it did. The combination of mid and late gave them the best output. So at this stage, the model was completely ready to revise all the experiments. The final conclusion was the model had 3 view encoders, CVA fusion with fusion location at mid and late stages, and complex model assigned to small tube size. And then they compared their results with the most analogous architecture that was there, which was slow fast. So they self-implemented the slow fast architecture using transformer only, and they were able to beat their architecture accuracy by a good margin. So now I hand over the presentation to Akashdeep for further studies.
Is my screen visible?
Yes.
So good afternoon, everyone. So we will be starting with the accuracy and computation trade-offs. So the authors have compared the MTV and the vivid factorized encoder at every model scale on Kinetics 400 dataset itself. And the vivid FE is using a tubelet size with a temporal dimension of t equals to 2, because that's the one that the paper has used earlier. And MTV is using a tubelet size of temporal dimension of t equals to 4. because with that they have achieved higher accuracy, and at every and the flops has been used less. Furthermore, we can now see that how the MTV B2 model is outperforming the L2 model of Vivid FE, which is basically in here. B2 model is a transformer depth of 12 layers, and the L2 model is the transformer depth of 24 layers. And while they have also used notably less flops, like the B2 one has used like around 480 something, and we can see from the graph the L2 one has used around 1000 flops. And now again, the similar behavior has been experienced in while the L2 model has outperformed the H2 model of like Vivid FE, where again the flops has been like there is an almost a 50% reduction or 40% reduction of flops. And now like this actually shows how we can achieve greater accuracy improvements by processing multiple views in parallel system. Now again, if we see the throughput comparison over here, we can gradually see that like with the models, when increasing its size, they are actually increasing its accuracy as well. So that's also one the thing we can note on. And now comes the now on like we'll be comparing on state-of-the-art results on Kinetics 400 dataset. So this was the comparison. They compared with a lot of models over here. And if you see the red box over here, this is what their model performed. And again, the number of flops that MTVB has used, which is the base model, is 4.79 teraflops, and which is like around a 40% reduction, which I told earlier. And then here is the with the web scale pre-training models, we can see this MTVL and MTVH and like all this pre-training where WTA's pre-trained data set has performed really well. So this was the one I was talking about. And now again, moving on to 600 dataset. On 600 dataset, one thing we have to note over here that the MTVB performance is second best to the MovieNet A6. This is because the MovieNet A6, whose model was actually structured like for Kinetics 600 dataset itself. So even coming close to that is a really astounding thing. And then again, with the pre-training data sets, they have really again outperformed. So which is nothing new right now. And in the Kinetics 700 data set, similar behavior can be noticed that they have already like over here. One thing to notice is that cover JFT is using a 3 billion data set with a and has achieved a top one accuracy of 79.8%, whereas the MTVH, which is only using the JFT dataset, has come close to 78%, and whereas the WTS dataset has actually outperformed the cover one. Now coming to the SSV2. In SSV2, we can again see that MTVB has like almost outperformed or come close to MWIT over here in the top 5 accuracy, and over here they have actually outperformed in the top 1 accuracy, where the MTVB with the higher resolution model. Now this comes the interesting part, where in the Epic Kitchen data set, we can see here they have compared in actions, verbs, and nouns. So in MTVB, in the noun section, they have actually achieved the state-of-the-art results in both the models, where in the with the base model and the lower resolution one. And in the action section, the higher resolution model has actually achieved the state-of-the-art results again. But for some reason in MovieNet A6, they have the MovieNet A6 has achieved much higher results than MTV-B in the verb section. So now in the moments of time, one thing over here we need to notice is that MTV-L has achieved the accuracy of 41.7% in the top one accuracy, and which is more than the VAT-L, and which had been pre-trained on how to 100 million data set. And not only in the top one, in the top 5 also, we can see the similar behavior. And obviously with the pre-trained one, they have obviously beaten the, like outperformed VAT-L. So now concluding that we can say that parallel like input actually takes less number of flops, increasing the depth of single view architecture is not worth the computation. And and we can say that they have achieved state-of-the-art results on 5 popular video classification datasets. And now, now we come to the limitations as stated by the authors. Like they performed really well in every set of kinetics, but there is still room for improvement, such as in the Epic Kitchen dataset in the verb section. And the models are actually heavily dependent on pre-trained large data sets. Whereas now for the future work, one thing that they can do is reducing the dependency on large data sets. And the second thing is, as the authors, they have conducted all these ablation studies on the standard transformers. They can actually try something more recent, such as the mbit or the swim. And now the innovations, according to us, the worth noting ones were the introduction to this, the concept of multi-view, stating the reason that multiple spatiotemporal resolution provides better reasoning. And if we analyze very carefully in prior research, we had seen that spatial and temporal understanding of those images was kept separately, and factorization methods were used to reduce the complexity. But whereas here in MTV, the authors are doing both granular and large scale understanding through the temporal patches only, but in different sizes. So, but one of the one criticism that we think is it is really computationally heavy due to usage of different encoders for different views. And now here are the references, and that's all from us. Any questions and comments?